Alright, silly people, here's the situation. We have a wave which is polarized, given by this polarization vector here. Um, and we are going to be scattering it off of a sphere of radius A, and we need to be calculating the scattering cross section uh, for the scattered wave using this equation here, which Jackson mentions in the problem statement. Um, the problem with this equation, though, is that it implies that the light is linearly polarized. So there's an implied um, dependence on the polarization of the light that you're sending in to scatter. Um, Here, where it turns out we're just going to be ending up multiplying the plus component and the minus component when applicable, and just summing over m equals plus or minus 1. Um, so for us, that's going to look like uh, 2 pi over 3, and then I'm going to combine k a to the fourth times a squared into or no, it's not k a to the fourth, it's k times a all to the fourth. That was a misprint there, but yeah, uh, this ends up being k fourth a sixth. We'll end up with an overall factor of 1 plus r squared on the outside, because we're squaring that square root term, they both share it. Um, but then we have to do the square modulus of the vector spherical harmonic stuff. So you're going to have a term proportional to x11 minus 2i n cross x11, but then also a term proportional to r e to the I alpha, all of this times spherical harmonic 1 minus 1 plus 2i n cross x1 minus 1. And you take the square modulus of all that stuff, which is a pain. So, just simplifying this stuff the slightest bit, I'm actually going to expand the square modulus in a big way. And I'm splitting it up like this, right? So we're going to have a term which is just the square modulus of all of this stuff, which is cross x11, and cut it off there. We'll have a term where we're just squaring the right-hand side of that square modulus, so r squared, and then the square modulus of x1 minus 1 plus 2i n cross, oh my goodness, my handwriting's terrible, cross x1 minus 1 squared. And then the cross term, which is gigantic, so it's 2 times the real part of this thing minus 2i n cross x11 dotted with the other term, which is the x1 minus 1 star minus 2i n cross x1 minus 1 star. So, okay, yeah, we have to work with this now. Just so I'm going to expand square moduluses again, square moduli. We're going to have an x11 squared, and then we're going to have 4 times the square modulus of the cross product of n with x11. And then we're going to have r squared times the square modulus of x1 minus 1 plus 4r squared square modulus of the cross product of n cross x 1 minus 1, and then the cross term of those things, which end up being 2 times the real part of I n cross x 1 1, the complex conjugate of that, times x 1 1, plus 2r squared times the real part of minus I n cross x 1 minus 1 complex conjugate dot x 1 minus 1. But then we still have the gigantic cross term, which we have to now deal with. Just leaving everything in there, we have 2 times, or I can factor the r out at least, plus 2r times the real part of e to the minus I alpha, and then I'm going to open a parentheses, and then I'm going to have an x11 dot x1 minus 1 star minus 2I x11 dot n cross x1 minus 1 star plus, or actually now minus another 2I, and this time it's n cross x11 dot x1 minus 1 star, and then also minus, or actually plus 4, because it's 2 times 2, and then it's n cross x1 minus 1. No, it's just n11 and then n cross x1 minus 1 star. Okay. And then I can close this up. And this up. Cool. Got a lot of stuff. Got a lot of terms. Gotta keep chugging along. Plus r squared. So all of these square moduli I'm about to do on this top row, Jackson already did, so I'm just going to use his results. All of them went like 3 over 16 pi times 1 plus cosine squared theta. And so I have a term which is 1 plus 4, and then I have a term which is r squared, and then I have a term that is 4r squared. Yeah. And then guess what? On this line as well, Jackson did all of this stuff as well. And I use those results as well. Those are just minus 3 over 4 pi times cosine theta. Then we had a term which was proportional to 2, and then plus 2r squared. Yeah, so 2 plus 2r squared. Pretty fancy stuff. We'll keep going. We need the real part. I'm going to use a property of the vector spherical harmonics. You don't have to believe me, and if you don't, just go check it yourself. But the x11, x1 minus 1 thing, okay, wait. If you take the complex conjugate of x1 minus 1, you get back x11. It's a symmetry property of this vector spherical harmonics. So I'm going to use that. So I got e to the minus I alpha, and now you just have x11 squared minus 2I x11 dot n cross x11 minus 2I n cross x11 dot x11. Noticeably, these terms do cancel out, so that is pretty cool. plus 4 times n cross x11, and then you square it. So that's pretty awesome. And then, okay, close that off as well. We're just going to keep trying to simplify this junk. We'll factor out a 5 from this stuff, so you get 15 over 16 pi 1 plus cosine squared theta. And that's just going to be 1 plus r squared after we do that. We'll factor out a 2 here, so it'll be minus 3 over 2 pi cosine theta 1 plus r squared. It's looking pretty good. We got plus 2r real part. This actually ends up being positive x11 squared minus 4 x11 squared, and so we're going to be left with minus 3 x11 squared. And I don't know why I wrote it on a separate line. I could have kept it all up here, big style. Okay. So factoring through the 1 over r squared stuff and also the 2 pi over 3, I'm going to get that all of these pi's are going to go away. First of all, 5 over 8 times 1 plus cosine squared theta, and then no 1 over r squared now. And then that's just going to be cosine theta. Yeah, just cosine theta. And then plus, still got a lot of stuff in here. So 4 pi r over 3 times the real part of, and actually not over 3, and minus, because I'm going to factor out the 3 inside the real part thing. So minus 2 pi r. That's it. And the freaking spherical harmonic squared. So I did just go and look up what the spherical harmonic was. I found it on Wikipedia, which sucks because I'm not going to be able to use Wikipedia on the exam that I have in a bit. It's just going to be 3 over 8 pi e to the I phi I theta hat I theta hat minus cosine theta phi hat. But then we have to square that and take the real part of the square. Yeah, take the real part of the square of that. Okay. 5 over 8, 1 plus cosine squared theta minus cosine theta minus 2 pi r. And I have neglected the fact that this has a 1 over 1 plus r squared. It's an important note there. That's going to be 3 over 8 pi. And then there's still a e to the minus I alpha in here somewhere. Yeah, I neglected to write it here, e to the minus I alpha, e to the minus I alpha. But then the real part of, okay, let me just collect all the terms. E to the, or times the real part of e to the 2I phi minus I alpha times 1 minus cosine squared theta. Okay. Then all in all, we have 1 plus cosine squared theta minus cos theta. That pi cancels out there. You just get 3/4. So minus 3/4 r over 1 plus r squared. The real part of the exponential will just give you a cosine. So cosine 2 phi minus alpha. And then 1 minus cosine squared theta is just sine squared theta. So it's this. And I think that's what Jackson got even. Yeah. Okay. Funny problem.